Hi, I'm Jacob Lee. I'm with the Google Code open source project hosting team, and I'm going to be talking about the Mercurial distributed version control system and how we got it to run on Google infrastructure. A point of administravia, this is sort of we are officially launching this to the public today, actually as of several hours ago, so you can go create projects, but after my talk. And if you're tempted to vanish, say during Q&A, I would at least lurk in the back until the end because we have t-shirts. So if you want one, I'd stick around. That's a great sound. All right. So I'm going to first talk about a little bit about project hosting and then a lot about how Mercurial is implemented and then about our implementation. So let's first time warp way back to the distant past where we still maintained source code in giant card catalogs. This is July 2006 at OSCON, 3 years ago when we first announced Google Code project hosting to the public. At that time, Subversion 1.0 was about 2 years old. One of the earliest distributed version control systems, Monotone, was a year older than that. Git and Mercurial were more or less sort of brand new. CVS was widely used, and I guess now we're dating ourselves well. And maybe several months before that, back in February, SourceForge had just announced Subversion support to add to its offering of CVS. And we came into that environment with the goal of using our unique assets, which is Google infrastructure, to provide rock-solid and scalable Subversion hosting, and thereby provide a platform for collaboration on open-source projects. And nowadays, there's lots of options out there for new and existing open-source projects. Google Code now has 200,000 or so give or take, projects, and several million unique visitors per day. SourceForge has expanded their offerings. They have shell accounts and several distributed version control systems and hosted track instances and cool things like that. And there are new players like GitHub and Bitbucket, which are specialized for a particular version control system and provide a well-integrated social experience on top of that. And that's all really great. We're happy that there are so many choices for projects out there, but we still think that Google is well positioned to support well these newly prominent features of distributed version control. So with that, about a month ago, we started offering Mercurial support to about 50 or so trusted testers, brave volunteers, and now it is open to the public. That's just a quick screenshot. So why did we choose Mercurial? This was a source of many great discussions. It was sort of entertaining if you like angry people. So, why would we choose Mercurial and not Git or Bazaar or many of the other systems shown on the previous slides? Any individual might have personal reasons to like one or the other. If you were to grossly overgeneralize, you might like Mercurial's simple orthogonal workflow. You might like Git's ability to do almost anything. Our decision was primarily technical and sort of unique to our situation. Mercurial has a really fantastic wire protocol that is over HTTP, and that is what Google is built on. Almost everything we do is HTTP, with a handful of exceptions like Google Talk, which is Jabber, XMPP. So that's something that was sort of unique to Mercurial. That is a definite. It makes it a very good fit for our infrastructure. That is the only stupid keynote transition I'm going to use in this whole presentation, but I had to because it's a flame war. And it's the point where people were starting to evade our +1 filters that we decided to make that issue read-only. Right. Okay. So if you're not familiar with, first of all, how many people here use, on, say, a day-to-day or at least weekly basis, version control? That's good. That's really good. If your hand didn't go up, you should consider it is an investment that pays itself in spades in time. So how many people use distributed version control? Nice, nice. All right. How many people use Mercurial? Pretty good. Git? All right. Fight? All right, okay. I stole that joke from Fitz and Ben, thanks. All right. So if you're not familiar, the basic workflow is you've got your, instead of being on some server somewhere, you just have your repository sitting on disk. You initialize it, you hack a bunch, and then when you feel you have a coherent change, that say like a single patch that you would mail out, then you just commit that, hack some more, and commit that, and you keep doing that. You build up your list of changes, and when you feel that you have something to share, which hopefully, if you attended Ben and Fitz's talk, is relatively early, then you push it out to some public URL. And then some other random person can come and clone it, and they get a copy of your repository with complete history locally on their disk, and they hack a bunch, and they can do their own commits, and they have something to share back to you. They push to their server, and that their changes are in red there. And then, meanwhile, you've done some more hacking, and then at some point you decide, oh, hey, so-and-so just emailed me with a cool feature. I'll merge it back in. So you get it from their repository, and now all of a sudden you have, at the front of your repository, you have a change and they have a change, and then you merge them in, and hopefully there are no conflicts, and then you have your, the tip of your repository, the single front point of history. And merging is something that is really scary, historically at least. You just don't know what crazy state the code will be in when you are done. That used to be the case, and one advantage of distributed version control is that this is something that happens all the time, pretty much any time you integrate a change that someone else did simultaneously with you, and it's relatively pain-free. So the other advantages is everyone, this person who submitted the change doesn't have to be a core contributor to be able to use the same tools that I do and have their own to keep track of history and so forth. And you can do this, so these two repositories can be totally equal, or your social structure might be set up so that one repository is considered central. You might have several central repositories, some more bleeding edge than others, but you're not constrained by technical limitations for how you choose to structure your repositories. And if you've tried to do things like sync from one repository to another in Subversion, it's sort of a pain. So this solves that problem well, too. So moving on to how does Mercurial actually implement this. So the first thing to note is that this repository here is not a linear list of changes. It's a graph. Specifically, it's directed acyclic graph. Internally, Mercurial might present to you a numbered list of changes, but those numbers are totally specific to your repository. Someone who integrated their changes in a different order might have different numbers. So when we were actually talking to other people, we identified changes by a unique identifier that happens to be the hash of some state of the repository. So we've got this graph here. Each node in the graph is a change set, a single patch, and the edges in the graph are ancestry relationships. We identify a change set by the hash of its contents, and the contents are enough to uniquely identify the change set. It is, the log message, the user, the date, a pointer to the manifest, which has the list of files, and the parents of the change if it is not the first one in your repository. So that's kind of a key point, because that means two changes that happen to touch the same file and have the same message, they're still identified by, they're still unique because their parents, which are different, are included as part of the hash. And so that means, because of all this, a single change set is entirely immutable. And this is a difference from other systems like Git. You can't change the contents of a change set without, if you say were to compress a bunch so it still represented the same final state but had different ancestry, then it has a different ID, which means it's a different change set because you identify them by ID. So this means that Mercurial really is not much a fan of rewriting history. There are extensions to do it, but it happens really before a repository has been published, typically. All right, so we actually have that the user-visible graph is the graph of change sets, but conceptually there are many others. I mentioned earlier that the manifest is the list of files in the change sets. That is also versioned in the same way that change sets are. Every time you make a commit, if the list of files changes, that is a new node in the manifest graph, with its parent being the previous list of files. And then each individual file conceptually has its own graph, which each time you change the file, change the contents of the file, it gets a new node identified as the hash of its contents. And then so you're building up these graphs here. The change sets point down to the manifests, and manifests point down to the version of the file at that particular point. And then to be able to do certain operations efficiently, you also have a link back up. Files and manifests have links back up to the change sets. So that's actually, it's a very simple model of history. A handful of other concepts that are good to know. The heads of the repository are simply the most recent change sets that do not have any children. Typically, at least in a public repository, there's exactly one head. It's a good state to be in. You might have multiple branches, which are just named heads, and, well, named heads coupled with their parent sets. And then you have tags, which is just a name attached to a particular revision, say for a release. All right. So how is this actually stored on disk? Mercurial uses a structure called a Rev Log that, if you've noticed, these graphs are fundamentally the same, whether they're operating on files, manifests, or change sets. So they're stored in a format called a Rev Log that is designed to meet the requirements of what Mercurial has to do, which is you have to be able to append to it because you need to add new change sets to your history. You need to be able to access it at random to be able to, say, walk the history of a particular file or to look up a file, a particular revision. And it has to be fast and it has to be compact. So there are two components to this file. You have, well, first of all, there is one Rev Log for each conceptual graph. There's one for change logs, one for manifests, and one per file tracked in the repository. It's divided into two components. You have an index and a data file. And to add a new node to one of these graphs, you simply add a new blob of data to the end of the data file and add a new record to the index. The index is just a list of fixed width records that tells you for a particular change set number or file number, what is its identifier, what are its parents, and importantly, where is it located in the data file. So the index tends to be very compact, such that you can, when you hit it a bunch, it tends to stick around in memory, and it's only 64 bytes per node. It doesn't take up very much space in memory. And so the data file, I sort of said that you just keep appending to the end of it, which is true. But if you're doing that for, say, a megabyte, a file that's a megabyte in size, each time you changed it, that would grow quickly. So you actually just store deltas in this file. You keep appending to a list of deltas, which would have its own problem in that to reconstruct the actual file, you would have to walk several revisions. And so the way Mercurial strikes a compromise here is it simply, once the size of the accumulated deltas exceeds the actual size of the file, it records a new snapshot. So typically, it doesn't have to read very many entries in this Rev Log to reconstruct a particular version of a particular node. All right, and so I just talked about all of that. Great. Writing to the repository is as I described, and the only thing is you do need to lock the repository when you're doing this so that you don't present an inconsistent state to any other instance of the HG command that happens to be running. All right. So to say make a new commit to the repository, we lock it, and we compute the list of modified files, which it has to be locked during that, and we show we invite the user to type in a log message, and then we write a new list of files, and then the new manifest, and then the new change set. We go in that order to make rollbacks easier in case the user cancels at some point. And so when I say it's locked, I mean, and then I say we ask the user to type in a description of their change set, it's very locked because that's a arbitrarily long operation. So this is only a write lock, so you can still read the repository while this is going on, but it's very much one operation at a time one write operation at a time on this repository. So those are all things that are just happening on disk, which is great. It's really fast, and you can do it on an airplane. To actually exchange with other people, the network options we have to do are pushes and pulls. That's how we exchange fragments of our repository, or more typically the whole thing, with other people. So to do a push is very easy, assuming that you are up to date with the remote server that you're trying to push to. I'll gloss over the case where you're not up to date. It's like doing a pull, then a push, sort of. So to do a push, you ask the remote repository, what are your heads? What are the most recent revisions in your repository? And then you find those in your repository because you have more stuff than they do typically. And then you say, okay, everything from that point forward is typically what I'm going to send you. And then you bundle that up into a change set and then upload it. It's a very straightforward and fast operation. Pull is slightly more complicated because there's this negotiation process where you have to figure out what the remote has that you don't have, so that you transfer the minimum amount. So the minimum amount is necessary is transferred to you. So in this case, I have the nodes in blue, and the remote has all of these new ones in yellow. So I ask, what are your heads? 3, 9, and 13. Oh, I don't have 9 and 13. Tell me about, what is some ancestry of 9? And it says, well, 9 follows a bunch of, it goes back until 6, and 6 has parents 2 and 5. I say, oh, good, I have 5. We're getting somewhere. And you keep going with this sort of 20 questions of figuring out what's the, what you need to get. And your goal here is to identify nodes 5 and 10. Those are the farthest back nodes that you don't have. And and then I tell the server, please send me everything from 5 and 10 forwards. And it bundles them up and sends. So there's a lot of, it's a little chatty at the beginning, but that's only transferring information about change sets. The actual change set, the potentially large operation is getting the actual data for getting the actual bundle of new data. But that is a single response from the server. So that is something this is what I am referring to when I say that it is well designed for our infrastructure, as I'll get to. All right, so how does our implementation, what did we have to do to get this running? Well, so there's good news and bad news about the way Mercurial is set up and how we're set up. The good news is we don't have to do commits and anything that the HG client would want to do to a repository, any extensions or something, because those all happen on the user's local repositories. We only care about the network operations, that is push and pull, and we care about whatever we have to do to support our web front end, the source browser. And we have to do very simple commits for the wiki, which project wiki is stored in a Mercurial repository as well. But other than that, it's mostly push and pull and some querying. So it's mostly just this DAG walking that I'll get to. So, but Mercurial makes a lot of assumptions that don't work for us. So, for instance, a single process is running on a single machine. It can access the file system directly, the file system, a single hard drive holding the Mercurial repository. It can lock it. It can load all of the index files that it needs into memory and do fast random access on them. Most of these assumptions don't work for us at all at Google because we've got sort of, well, see, here's a particular Google cluster, right? That's actually a picture of it, one of the first Google server environments back at Stanford. But we tend to have racks that look like that. We have our whole infrastructure is built on the assumption that we have lots and lots and lots of relatively cheap computers. We would used to say commodity computers. They're not strictly commodity. You're not buying them from Dell or anything. But they're certainly not the beefiest servers that money can buy. We have, on top of that, we have our layers like GFS and BigTable, which I'll talk about. The whole point of this is that when you've got the volume that we do, you're going to have lots and lots of computers anyway, and as soon as you have lots and lots of servers, you're going to have failures all the time. And so there's really no point in over-engineering because you'll still have failures and your software will still have to handle them. So we prefer just giant clusters and write the software as robustly as we can to operate on them. So the first layer for that is the Google file system, GFS. It was built way early on to serve the needs of search. So the primary need that it has to be robust in the face of random computers or racks or data centers vanishing. It has to hold hundreds of terabytes, and these numbers probably are all low balls, pro tip, and multi-gigabyte files. And it has to, the unique workload of search is you need to be able to stream these files really fast, like say you're running a MapReduce, a computation across them. So you just need to be able to stream it really fast, and you need to append to it very fast. And you need to be able to append to it concurrently. Say you have lots of workers all appending to the same thing. They need to be able to do that without stepping on each other's toes. And maybe you need to do random access, but it's not your primary workload, and it needs to be possible, but doesn't need to be fast. So there's a system called Google File System. It's published. There's a paper about it. It's not open source. But it's a single master system, just to keep the implementation sane. And then it farms out. It divides a single file into multiple chunks that are 64 megs each, farms those out to a bunch of servers, multiple copies. So it might be 3 or 4 copies of it per machine, or on separate machines. And then you always query the master, hey, where can I find this file? And it tells you, oh, there are chunks here, here, and here. And then you hit the actual file servers. And those might, if they die, then you go back to the master and ask it again, and eventually it keeps it in sync. But so would we just, well, that actually sounds sort of attractive. We need fast appends, but so will we just build straight on GFS? No. And actually most teams at Google don't do that because, first of all, GFS doesn't handle replication between data centers, and we like keeping our data in more than one data center. So if one vanishes from the face of the earth, we don't have to go and tell people, hey guys, all those repositories we were holding on to for you? So that would be embarrassing. So we don't want to have to write that ourselves. We need to be on top of GFS. And also, the performance characteristics are, sort of quirky. And this whole, for instance, if you need to fetch a byte from a file, you have to swap it in 64 megabyte chunks, and that's sort of suboptimal. It would not jive very well to simply have the Rev Logs correspond to GFS files. It would have saved us a lot of coding, but it wouldn't have worked. So on top of that, there's BigTable, which is the primary database technology used at Google. It's used by lots of teams. It is not a relational database. It is sort of a row-column database. It is built to meet the diverse needs of many Google teams. So it has but the primary example, is in the papers about it, tend to deal with search. Imagine that. So your rows are just arbitrary strings that are lexicographically ordered. Those are a single table, which is ginormous. It can be ginormous. So it's chunked out to different servers according by the row space, so different sections vertically, and then or horizontally. Yeah, the columns are also arbitrary strings. So it's sort of you end up with this sparse matrix where you don't have to have values for every column, and they're grouped into families. So also for locality of access, and then the values you actually store. Well, it might be a single value per cell. It might be a list of values by timestamp, which is a feature that we're not too reliant on, so I'll gloss over it. And the actual values you store are opaque blobs. There's no sort of, referential integrity or SQL-like thing going on here. You're just storing blobs in this. And now that it's open source, we can talk about this. These blobs often are protocol buffers. All right. So the operations that you do, you look up by a particular row and column name. You might scan a set of rows, and you might, of course, write to it. And you have the ability to lock a particular row to write values into it, which is important. We care about that. And this also, it's not open source, but there's a paper about it, and the Hadoop project from Apache, I believe, has an open source implementation of a BigTable-like system. So BigTable is what we would like to build on. It's widely used inside Google. So it turns out that we've got all these things indexed by hash. That is a very good match for BigTable, which we can treat essentially as a giant hash table with some other features. So those change sets that we identify, these nodes in the graph, which might be change sets, might be particular versions of files, we store those in our row space identified by this hash, by the repository name, and by what kind of node it is. The C there is for change sets, the M is for manifest, F is for files, and if it's a file, it's also identified by what's its path. So this, because as I mentioned, these are sorted lexicographically, so this has the advantage, and they're split into tablets where each where rows that are close together are likely to end up on the same machine and can be accessed very efficiently together. So all the change sets for a single repository end up next to each other lexicographically. Same with the manifests, same with the different versions of each file. And then, so the values that we store split up into these column families here. So for files, we store the contents of the file, obviously enough. We actually fragment them because there are row size limitations in BigTable, but we can still retrieve those linearly by row. And then for manifests, we just store the list of files, and for change sets, we store the change contents, the log message, and so forth, just basic data and metadata. And so that's all just the raw contents of the graph that we throw into the table. And so I actually identify a single repository. We have its own row, indexed by repository name, and it has simply the list of heads that refers back to the change sets stored in the table. So that which is enough to uniquely identify the current state of the repository. So for the operations that we actually want to do and why they are efficient, this is, first of all, to clarify, this is, when I say push and pull here, this is all from the client's perspective. So if I'm pushing something into Google's servers, well, all we have to do when we receive this incoming graph data is just shovel it into this row space we talked about earlier, and it's all sort of, it's garbage, it's unlinked, it's not referenced anywhere. So we are free to do that without acquiring any sort of lock because it's not messing up the current state of the repository because we haven't changed the list of heads. So once we were done with all that, we've noted what we think the current heads are in the repository. And if that's still the same, that means nothing else has happened to this. So we can go ahead and lock the repository row, check to make sure it hasn't changed, and then write the new list of heads that we computed. And then we're done. The repository instantly refers to this new data we just added to the table. And that's all something that can be done if you have multiple pushes going at the same time. They pretty much all succeed, and they all happen in parallel. One of them will win for this actual very small write at the end for the repository row, and the other one will have to do a little more computation before it can update that row again, but it still gets to succeed. Now, if the client is pulling from us, we have to answer that game of 20 questions that I described earlier of the repository, of the client asking us, well, what do you have? And so that is mostly just tracing back the history of the repository in this table. We look up a change set, we look up its parents, keep going until we find the information the client wants. And then once the client has identified, okay, I want you to send me everything from these two changes forward, then we can get the actual change set contents from the table and then stream those out to the client. That is, so at the beginning there's some graph walking, but to actually read the change sets and build up this bundle, that is something that we can rely on BigTable's parallelism to just, we basically can send them out to the client as fast as we can read them. And then the last major operation we have to do is for the source browser, the graphical front end that we've written. And that is things like getting the next and previous revisions of a file and getting the history, or at a particular path, getting the next and previous revisions, getting the contents of a file at a particular revision, that sort of thing. That is all just graph walking, so it's, well, we'll get into the performance of that. The results that we got, well, there's a lot of optimizations that we can do that are, or really that BigTable does for us. The thing we need to avoid is doing a sequential read or write, which is ask BigTable for something, wait for an answer, ask it for something else. Because Mercurial is sitting on a local file system, it can do that very quickly, and it's typically, it'll all be in memory. And for us, that is maybe a, 20 millisecond round trip each time. So our goal is to let BigTable do the concurrency. We throw all of our, if we have writes we can do in parallel, we throw them into a pool and wait for all of them to finish, and BigTable gets back to us eventually. Same with reads. And then we do a little bit of pre-computation to minimize this graph walking for things that we know the client is going to ask us. It's going to ask, hey, for this particular node that I don't have, what is the farthest back node before a merge? Because that's a single line of history that it's going to want to investigate further. So that's the sort of thing we can pre-compute because it's all in the past and it's guaranteed never to change. So we can just store it when we do the writes. So the actual results we get from our implementation, when the client is pushing to us, that is ridiculously fast. We just accept data and writes into the table, and because there are many, many machines involved here, this can happen way faster than an actual file system write. The pull, that negotiation process at the beginning is still a certain amount of synchronous reads where we have to wait for an answer, and that's something that even we can't do anything about a lot of those round trips. So even at the best case, once we're finished optimizing our implementation, we might still be, say, twice as slow as Mercurial because of the difference in architecture. And then for the source browser, we're very fast for certain operations. Retrieving a particular revision of the file, that's just a table lookup. Retrieving the history of the file, so in Mercurial, that is just tracing a single Rev Log that holds the whole contents of a file. That's slow for us because we have to do a whole bunch of graph walking, and that's something we're working on. You'll notice that's slow in the web front end, but we have some stuff we can do to make it faster still. But overall, though, so those numbers for a single repository also hold true for however much we want to serve. a single job running in a data center, we can serve hundreds of queries per second on the source browser across all sorts of repositories. And for the pushing and pulling, we can do tens of megabits per second from the single job, which is rather fast for a Python program on a single computer. So as we don't run into things like lock contention as much as you would if you had the stock Mercurial server trying to do that sort of thing. So the lessons we can learn from this is, engineering, it's really about trade-offs, and there are things that the design goals very much affect the end product. Our design goal is that if the entire project hosting ecosystem, if all of Google Code decided to switch their projects today to Mercurial, we could handle it maybe by throwing a couple more computers at it, bring up a couple more jobs in. We can handle the traffic fine. But at the same time, that involves a lot of when you're sharding things across computers like that. There are certain operations that you're not going to be able to do as fast as if you just had a single process talking directly to disk. So that is the scalability there will always have a price. So that's something that when you're starting to design a system, these are the things you need to keep in mind. And one more cool thing that we have, I think that's a Lego clone army, I don't know. So you notice that, we'll go back to this, all of that data in that top table, that's all immutable. And one thing that's very common in a distributed workflow is having multiple copies of this more or less the same repository. And that is, for Mercurial, that is something that if you want to clone a local repository that's sitting on disk, it doesn't do any work. It actually hard links the new repository to the old, and then when you actually do a write, it then goes, whoa, this file has 2 references to it. It's linked somewhere else, and then it actually does the copy then. So cloning is wicked fast, but I should stop doing that. But it's will slow down your operations randomly later. So it's it works. We can do a little bit better than that because all that, if we were to clone a repository on the server side, all that actual revision data that's stored in that table, that's all immutable. And whatever happens for the divergent history of these 2 repositories, that data can remain shared. So the only thing that uniquely identifies a repository is that list of heads and the list of branches and things like that. And also, if we have any sort of references pointing forward that we've pre-computed, those are things we have to watch out for. But the bulk of the data is shared. So that's something that we can certainly do pretty easily from a technical perspective. Getting the right UI and integration with our existing project hosting is something that will take more effort, but it's something that you can look forward to in the near future in your projects. And we believe that the distributed workflow, it's not really just, you don't want to be able to use Mercurial, though you might enjoy using Mercurial. You want to be able to take advantage of the workflow of distributed version control, and that's what we hope to support. Thank you. Any questions?
Kind of unrelated, but we are always looking for ways to let our graphic designers store big Photoshop files. Kind of doesn't work in source control, but they're I've never seen another solution. We want revisioning in that process, but do you have any solutions?
Write one and tell us about it.
No, you're Google. You should know things.
Well, actually, for projects that are doing this, we recommend using our downloads server, which you can at least give, revision numbers. You have to do it yourself. It's a pain, but it's doable. And that is relying on a totally different massive storage system.
All right. Well, maybe we'll start an open source project.
Hi. You talked about the change sets sort of having a similar hash value, and then that's why they hash together close to each other. Is that?
say a change and its parents will have totally different hashes, right? Because it tries to be a reasonably smooth function, or reasonably arbitrary function. But they all have the same prefix of the repository name and then C, as opposed to, say, the files or manifests that are also stored in the same table. To be clear, that was all one big table.
Yeah. So I mean, so my question is more probably related to BigTable. So this sort of the same prefix hashing to similar locations, is that something that is by default in BigTable, or did you have to do something for that?
No, that's how it works. Rows are stored lexicographically and then sharded by the prefix.
So it's a location preserving hash table, is that?
Sorry?
Like, I mean, BigTable is like a location preserving hash. I mean, it preserves like, I mean, based on lexical.
No, it'll just, it'll start on one tab, and then when it gets big enough, it'll split it up as it deems appropriate.
Thanks.
Yeah. It's not something we really have to deal with. It's BigTable magic.
I was just wondering if you imagine Google eventually using something like Mercurial for its own internal development, and compared to big systems like Perforce have trade-offs. Could you talk a little bit about what those trade-offs are and what systems like Perforce do better or worse than Mercurial, and sort of how you think that through?
Well, we're sort of unique at Google. We have our basically one giant repository for like everything. So Perforce scales, crack engineers whom I don't know who they are do a good job of scaling it. And so I don't know actually if there are any developments on that front.
I've been trying to evaluate the different distributed version control systems, and one of the big things in my environment is being able to import existing Subversion repositories into whatever it is. And I ran into quite a few problems using Mercurial and such. I've been kind of leaning towards Bazaar, and I was just wondering, what was your experience with that, and how poorly did it go, and that kind of thing?
Well, the actual import I found is straightforward. Getting all of the correct bindings is a pain in the neck right now. You have to get the Subversion Python bindings because Mercurial is written all in Python. That's kind of the most annoying one. If you have, say, a recent Ubuntu distribution, you might have it all out of the box. Otherwise, you have some compiling from source in your future, and that's loads of fun. So that's something, it would probably be, GitHub, I know, actually has some sort of automated imports for our existing Subversion repositories, which is really cool.
Do you offer transition from Subversion to Mercurial currently?
Yes. As of this afternoon, you can select from a little drop-down which system to use. But unfortunately, you do have to do the migration yourself, which we know is annoying.
I was just interested, can you extend this concept to content repositories? Like, say, does Google Docs also use similar version systems?
Sorry?
Like Google Docs, does it use BigTable for its content?
Oh, I don't know what Docs uses. A lot of teams at Google use BigTable, but Docs and sites all do versioning, but they're certainly not like using Mercurial or Git behind the scenes.
I was wondering about your experience while changing the, let's say, writing or disk backend of Mercurial to work with BigTable. If you're, for instance, going to release these modifications to Mercurial to public as a first partial question, and then what's your opinion or your advice? Because I'm very interested in being able to change that backend instead of writing directly to disk, writing, for example, to a relational database.
Oh, that'd be fun. It turns out, so we're not, that fundamental structure of the Rev Log, we had to totally replace that. And that's sort of the bulk of the interesting operation. That, coupled with us only dealing with the network operations, means we use a little bit of, say, like the parsing code, but most of the actual implementation is internal. So it'd be something that's sort of challenging to open source because of the dependency on BigTable, but I hope at the very least you can expect maybe a white paper or something from us, if not a subset of.
I was mainly thinking about just maybe a small abstraction layer where you can hook your, let's say, it's persistent strategy of the Mercurial.
The Mercurial code base is relatively clean. It'd be sort of doable, but you have to keep in mind your access patterns are going to, or your performance characteristics are going to be totally different. So if it hopes to be able to do random access by integer alias for change sets and do that quickly, you need to be able to support that. Which actually, in say a stock relational database, probably would be doable. We don't use integer IDs, anywhere in our implementation. It's only hashes, so ours is pretty quirky in that. So.
Okay, and just a very small question more. Do you support for subtree cloning or exporting? Yeah, I mean, instead of the full repository, just the subset of the path.
No, I don't think Mercurial does that. at all.
Mercurial does not.
Yeah, no, so we don't either.
Okay,
it's not in the protocol.
Hi, a lot of CM systems set up at the beginning to facilitate the rest of the engineering process. Do you have any plans to integrate or support continuous integration on the back end, tying into bug systems where you can track changes both in the issue tracking system and in the code system linked together?
Some of that is possible right now. We support webhooks, so when there's a new commit in the repository or a new push for Mercurial, we just hit an external URL. That URL then could get that revision and run, say, a continuous build from that. It's something that it would be sort of challenging for us to support internally because every build system is so radically unique. So that's the best bet for now.
And what about integration with bug tracking?
What sort of integration?
Well, a lot of well-developed CM systems have this notion that you have a change, and the change incorporates both the code change and the issues that are associated
Versioned
with
issues.
it.
No, we're
not versioning the issues, but tying the issues together with the source code changes.
We have some integration where if you your commit includes commands to the issue tracker, like fixes issue number 23, it will actually close issue 23. So that's sort of most of it. All right. Thank you. We have T-shirts.